First one we're going to deal with is some trig identities. So probably one of everybody's favorite chapters usually is remembering all those identities, proving them, all that good stuff from your previous years. Here are the 5 that I would strongly suggest that you get down pat. One of them I have a little typo as I now look at this. I look at my key. This tangent right here, I'm sorry, cotangent right here should be cotangent squared. So add that in. Otherwise, you're going to be learning some wrong stuff there, and that would be bad. So most of those should look pretty familiar. Number 1 is probably the most common one we're going to use. The secant squared identity is pretty common. But think about sort of why we're picking these. It's because we know the antiderivative of these. Okay, we know the antiderivative of a secant squared. We know the antiderivative of a cosecant squared. Those are things that we know the values of or the antiderivative of. So these you're going to want to know pretty well, because let's say we now come down to here. And what I want to kind of make sure, making a point of emphasis is, don't think U substitution doesn't work anymore. As we get through this chapter, the partner assignment that I have on the calendar, usually when people do that in class, everybody just forgets about U substitution and they try to do all these new methods that we're going to use in this chapter. U substitution is still going to work plenty of times. So if we look at number 1, U substitution is the route we're going to take. So just kind of hit that point. Don't think that we can't still do U substitution. That's actually your first option if we can't just look at it and know our antiderivative. Because if I let U be the sine of x, the du is going to be a cosine of x, and then our dx. And that then allows us to rewrite this integral as u cubed, and then this cosine of x dx is a du. So very quickly, without having to do any of the new methods, we can do U substitution. Pretty simple little antiderivative, u to the 4th over 4 plus your constant. Throw in what we found our u to equal, or what we set our u equal to, and then that's our answer. All right. So don't now treat U substitution like your redheaded stepchild. All right. However, we will now get to. Sorry, Emma. Emma smiled at that. I like redhead. It's cool, I think. So number 2. If I now give you number 2, there is no substitution here in regards to U substitution that will do us any good. If you think about what we have here, the only real thing we could let U equal is either an x, which doesn't do us any good, or a sine of x. And then when you take the derivative, you get a cosine. There's no cosine involved. So U substitution now does not work. If we look at our steps that I have listed, and this can be somewhat challenging just because I think the next few methods we're going to do, you're going to think are easy. This is usually one of the ones that people find a little more difficult because there isn't this mechanical way that you're going to do every single problem. There's a lot of thinking. What identity do I use? Once I use an identity, what do I do from there? But step number 1 is you then kind of figuring out, and it's sometimes a little bit of a guess and a check, what substitution are we going to use from the list above that will allow us to rewrite this integral? Okay. So there's a lot there in step number 1. All right. And if you look at this guy here, so here's some general rules, and I don't list them in our steps because these are general rules. They'll work more times than not, but they don't always work. If you notice this odd power and you compare that to the list that I have up here, notice how these all have powers of 2. So if we want to get anywhere with any of these identities, we probably need to get some trig functions squared. So to get that taken care of, I'm going to first rewrite this as a sine squared of x times a sine of x. It's still a sine cubed, but at least now us getting this sine squared expression, we can now look at our identities and have some substitution ideas. I start with the one that's the most obvious that everybody would want to do because this is the one that everybody remembers every year, and this is the sine squared plus cosine squared equals a 1. So that's the one that we're going to use. So think about if I had you solve that for sine squared. Wouldn't sine squared be 1 minus a cosine squared of x? And then we'd still have that sine of x dx. So our first general rule is we want to get some trig functions to the power of 2 because that's what all of our identities deal with. The second thing that is nice, eventually this does turn into U substitution, so you're still going to probably have to do U substitution. The other general rule, if we're going to let U equal something, pen's behaving badly here. then you have to think ahead again to the step of creating a derivative that we also would need. So creating what I would call a singleton trig function. So see how this guy is just a regular old sine all by himself? There's not two of them. There's not a power of three. It's just a single sine of x. The nice thing about that is if I now come over here to this function, the way we're going to approach this, and again, I'll give you an opportunity to kind of figure out what you're going to be doing here shortly with some of these. But right now, we're going to let u be cosine. The nice thing about having a single trig function right here is when we take the derivative of whatever we're going to let u equal, notice how it's going to give us that sine of x function that we need. What we're looking at isn't a negative sign, however, so same thing with our u substitution. We're going to take that negative, you're going to divide that over, so that sine of x is actually equal to a negative du. Go ahead and substitute what we now have. So we never got rid of the 1. We still have our minus sign. The cosine was our u, so this should now be u squared. The sine of x dx we created over here. So the sine of x dx that we need to get rid of here, we have, that's equal to a negative du. And then similar to u substitution, we know we did the substitutions correctly if we have everything in terms of u now, and we have something we know the antiderivative of. So when we look at what we now currently have, we should look at that and be like, yeah, that's a really easy antiderivative. That's something that I can now do. That would tell us that we probably did our substitutions correctly. So now take your antiderivative. I'm going to distribute the negative as I do it. So I'm going to get a negative u plus a u cubed over a 3, and then plus your constant. Unless there's limits that we have to plug in, since we start in terms of x, we want to end in terms of x. So our final answer then, replace your u with what we let u equal. And this is then your answer. Something just popped in my screen. What was that? Oh, who is that? Vanchi. Question?
Yeah. Why did we not use number 5 for the...
Why did we not use number 5? Oh, the identity up here?
Yeah.
Good question. We could try. So what was that? So we had sine squared. This is a lot like u substitution in the sense that it's a little bit of guessing and checking, especially early on. Even some of the ones that I look at, I don't necessarily know right away. It's just, okay, what identity could I use? Look ahead a step or two. Is this going to work out well? So if we rewrote this and you did decide, all right, well, here's a sine squared. Why don't I try that? 1 minus cosine. And some of these you can do more than 1. So if I now rewrite this as 2, right, 1 minus, yeah, I got to remember these identities myself. And then we'd still have the sine of x dx. All right. So this actually might work now that I look at it, which is fine. I'm going to pull the 2 out. So then I'm going to be left with this. No, it's not. All right, so let me show you why this will not end up working. Our issue is going to be, if I have this 1/2, let's say I let the u equal this cosine of 2x. Here's going to be our problem using that identity. When I take the derivative of this, it's going to give me a negative sign, so it's going to give me that sign, but notice how it's going to give me a negative sign of twice x. Is that the composite of our sign down here? No. So there's no way we're going to be able to, and if I let u be sine of x, the derivative would give me a cosine of x, but I would need a cosine of twice x. So the fact that those composites are different would prevent us from being able to use that identity. Okay? But that's a really, really valid, good question, because you just don't know when you approach a problem which one is the correct one. So you're probably going to pick some wrong u's more or identities more so in this than you would have in the past. Right? Yeah, good question. All right, let's hop to number 3. Number 3, go ahead and, okay, so that's good. Yeah, we've done 2. See what you think about 3. See what your first thought would now be. then what I would hope you would kind of recognize, because here's what I'm guessing most of us, well, what most of us did. Because for most of us, sine squared plus cosine squared equals 1 is the one that we know, that we remember. So most people probably rewrote this as a 1 minus a sine squared of x. But think about what you've kind of just done. Didn't we just really replace a cosine squared that we don't know how to handle, that required a substitution, with a sine squared? We basically just created the exact same problem, but instead of a cosine squared, you'd have a sine squared. So while there are ways to approach it if we did this, because we do have an identity for sine squared at the top of the page, that might work. Why would we do that when we also right away had an identity for the cosine squared at the top of the page, other than the 1 minus sine squared? So if you look at number 4, let's try that one. So where cosine squared of x is equal to 1 plus a cosine of 2x divided by 2. Totally up to you how you handle it, but kind of what I did at the top of the page when Devanshi asked her question. I'm going to pull the half out. You could split this up if you want, write 1/2 plus cosine of 2x over 2. That's fine, nothing wrong with that. But I'm going to pull it out completely. So then I'm just dealing with a pretty simple little function now that I'm going to try to take the antiderivative, because those both then are pretty obvious, which then tells us that we're ready to go. We don't have to do u substitution here, just the initial trig identity worked for us. So we're going to have our 1/2. I'm not going to distribute just yet. The antiderivative 1 is x, and then I should get sine of twice x, and then divide by 2, plus your constant. So that our final answer, we would get 1/2 x plus the sine of 2x over 4, and then plus that constant. All right. All right, number 4. If you look at number 4, it's very, very similar to number 1, where number 1 we were able to do u substitution. But that little cosine squared now creates a problem. So no matter how hard you try, if we tried to do u substitution with number 4, like in number 1, we just said let u be a sine of x, and then that du would have given us a cosine of x. Our issue is we need 2 cosine of x's, and we can't get that from that substitution. So no matter how you try, u substitution right from the get-go does not work. Okay? So another general rule, you may be tempted to rewrite this cosine squared as a 1 minus a sine squared. But here's our issue. At some point, you're probably going to have to end up doing some u substitutions. And if we have a bunch of sines everywhere, wouldn't it be nice if at some point I'm going to let u have to be a sine of some variety, whether it's sine, sine squared, whatever? Wouldn't we then eventually get a cosine down here? So we don't really ever want to put these all in terms of the same trig function. So we don't really want to write this guy and create yet another sine function. So what we're going to do instead, we want to start breaking this guy down. So I'm going to write this as a sine squared of x, and then a sine of x. And then we'd still have our cosine squared of x, and then the dx. Remember how I talked about it would be nice to create a single trig function so that our du would take care of that singleton. We're close now, so what we're going to try and do is I want just this sign to remain. And the way I'm going to be able to do that is I'm going to take my sine squared. I'm going to rewrite cosine squared as 1 minus sine squared. No, sorry, wrong way. Don't do that. I want the sign to be the singleton. I want to rewrite this guy. See, this is not obvious stuff. So I'm going to rewrite this as 1 minus cosine squared. And then I'm going to write the cosine squared that remains next. And then I'm going to put my sine of x dx at the end. The order doesn't necessarily matter. I just like to put that at the end for the visual. Now that we have this sign all by itself, that kind of guides us a little bit to where now let's let our u be a cosine of x, because doesn't the derivative of that give us a sine of x? I talked about this when we did u substitution a while ago, that sometimes you want your u to be, so notice how we have a couple different places where we have a cosine. Sometimes you want our u to be one of them, sometimes you want them to be both of them. We haven't encountered one yet where our u substitution is going to be both of the functions until now. So what we really want to say is, we want this to be 1 minus u squared. This is also your u, so you're going to have another u squared. And then what we would need to get rid of is the sine of x dx. And we can do that because when I take the derivative of cosine, that's exactly what is, whoa. All right, let me try that again. Interesting. So take the derivative of that cosine, and then that should give us a negative sine of x dx. We just don't want that to be a negative sign. We'll multiply the negative over to create positive sine of x dx. So to now get rid of this, the sine of x and the dx, we have created that. All we need to do to get rid of that is replace it with a negative that I'm going to put out in front, and the du I'm going to put behind. As long as we now have something that we can handle, we have everything in terms of u, then we should be good. Now, what I would recommend, and we could have done this before, so the order in which you do some of these things could be different, but in this case now we want to distribute, so this would become u squared minus u to the fourth du. And then from there, super easy in terms of our antiderivative. Again, we can't integrate products, so at this step right here, don't be trying to do the antiderivative of this times the antiderivative of this. Won't work that way. Distribute first, and then now we're all set. So this should be a negative u cubed over 3 plus a u to the 5th over 5 plus our constant. Replace your u with cosine, and then that's our answer. Okay. All right, number 5. As you're looking at that one thinking, there's no way I would ever get that on my own, go to number 5, because number 5 should build your confidence. So go to number 5, go all the way through number 5, and show yourselves that not all of them are that hard, not all of them are that involved. You can do number 5, especially with the formulas right in front of you. And try to go all the way through that and see what you think. All right, hopefully we're getting pretty close. There's only one option, correct? So you don't really have a whole lot to choose from. That was number, 2? You have to do a little bit of solving for the tangent squared. So if you actually solve that for tangent squared, what tangent squared would have been equivalent to is secant squared of x minus a 1. And then hopefully you understood, we don't need to do u substitution. We don't make this any harder than what it needs to be, because don't we know what we took the derivative of to get secant squared? Right, that's a tangent. And then definitely the antiderivative of 1 is an x, and then that's our answer. Okay. So there are certainly some where it's just a direct substitution and you're ready to go. 6, however, is not one of those. 6 I would consider a harder type of a question. So try to get 6 started. See if we can kind of at least pick an identity, go with it, see if we can create something that might work. This one I would consider a harder one. see where you're at. If I put you back at number 4, so if you kind of look here, I didn't necessarily do it with this one. We distributed at the end, but we could have if we wanted to. We could have taken this and distributed it right away. We said there's some different order in which we could approach some of these problems and it's still going to work out, because if I distributed, I could still let my u be the cosine, and I would get u squared minus a u to the 4th. And then the derivative of this would have given us this negative du. I still would have gotten the exact same answer that I got if I had distributed that. Here it was optional, it didn't matter. When you do number 6, hopefully we did this. That's pretty much a standard rule that you're always going to want to do. The cube doesn't do us any good, but the squared at least gets us started with something. You only had one identity. It's the same one that you would have used in the previous problem. So secant squared of x minus 1, and then our tangent of x. What tends to happen is people kind of try this one on their own, and I'm usually able to kind of walk around and see what's happening. A lot of people will pick tangents because they realize the derivative of this is secant squared. The issue with that, and the reason it doesn't work, we don't just need a secant squared. If this is one expression, one term, we would need to get a secant squared of x minus 1 if we do our substitution right there. So, good stuff. It just doesn't yield the derivative that we want. So what I was hinting at with number 4 when I just showed you that is, this one, in order to make this one work, now we do want to distribute. We want to take this tangent, and we're going to distribute that inside of those parentheses. Then, an old rule that we talked about that we rarely had to do, because it's usually unnecessary, is we said if we ever do an antiderivative of a sum, we could if we want, and most of the times we don't want to, we could split this up into 2 separate integrals. It's usually pointless. What you're going to find with these, it's going to happen a little more often, because the way we're going to do the antiderivative of this guy is different than the antiderivative of this. So in this case, I would suggest splitting these up. So this will now become a little bit more of a common occurrence. So be prepared to do that some. Whether we remember it or not, because this is not one of our more common ones, we have done this, correct? Whether you remember it or not, you remember us having talked about the antiderivative of tangent. So that guy's ready to go. Then we just got to recall what it is. All right, so we'll get to that in a second. This one now is u substitution. So this is the substitution that a lot of people go with at the beginning. So couldn't we right now let u be a tangent, du be secant squared of x dx, and then that works out perfect for this one. So this substitution, here's your u, tangent was the u, secant squared of x dx is your du. So now we're good with that. And then we'd still have minus whatever the antiderivative of tangent is. The next step then is largely our answer. You'll do your antiderivatives of both. So u squared, u squared over 2. It's up to you how you want to handle this. Negative, so I'm going to pretend the negative is isolated. And then if you recall, the antiderivative of tangents was a negative natural log of cosine of x. So if you treated this as a negative tangent, then you just get a positive overall. So final answer for all of that. U was a tangent, square root of x over 2, plus the natural log, absolute value cosine of x, plus our constant. That's pretty rough stuff for the first time seeing all of this. Okay. Good with that, hopefully. All right, number 7 then. First thing you're going to want to do here, we don't necessarily want to rewrite anything yet. There's no identity for the tangent plus secant squared. But if we actually do just square this binomial, so if you square the binomial, so that's us squaring the first term, then if you remember, it's twice the product of those 2 individual terms, so 2 times tangent secant and then we square that secant term. Then a lot of good stuff should have just happened there, correct? When by squaring this out. 2 of the 3 are ready to go. Even though the order is kind of messed up here with the way that it was written, don't we know the antiderivative of secant tangent? We haven't had to deal with it in a while, but we know what we take the derivative of to get a secant tangent. So that guy's ready to go. This we have just done recently. The antiderivative of secant squared, we also know. So our only real issue is the tangent squared. And we've already done tangent squared, but let's say we haven't. This is one probably that you're going to want to split up again, because this is not ready to go, and then the other 2 are ready to go. I'm going to rewrite this as secant tangent now as well, just so it's more obvious. Now, the tangent squared should be really easy, correct? Because we've already done it today. I don't know what number it was. It was number 5, the one directly above it. So that you can really just kind of model off of number 5 above. That one you need the identity for. And then the other one, we can do this really at any time. If you want to do the antiderivative right now, you could. But now that they're all ready to go, now we'll go through this. So the antiderivative of secant squared is tangent of x minus x plus 2, and then the antiderivative of secant tangent. Hopefully we remember how that was secant of x, correct? And then the antiderivative of secant squared, we just did over there, is a tangent of x again, and then plus your constant. We have some like terms, so I would expect you to probably do that. So we have 2 tangents, 2 secants, subtract your x, add your constant, and then that's our guy. All right. Okay, we got one more. All right, last one. See what you think for the last one then, since we got a little time to burn. Take a minute or 2, see if we could get through that. All right, we're about 50-50 in class here, and I usually like to walk around and kind of snicker at people when we're doing this problem. I deliberately put this one last just to kind of drive home the point that don't neglect U substitution and always jump to these new methods. Because this guy, you could maybe, I'd have to play around with it. You might be able to get through this with substitutions. However, this we could have done before today with just regular old U substitution. Because if I let U be a tangent, and then du is a secant squared of x dx, Then this here is just u squared. Secant squared x dx is du. And now we've created a really simple little integral that's written in terms of u. That means we do our antiderivative without a problem. That's easy. Replace your u. And then that's our day. All right. On the test, even on the, you have a partner assignment you're going to do a little bit later when we put all the integration methods from all year together. Always check u substitution first. Don't fall in love with all the new methods just because that's what we're currently doing and you think all of them are going to be that. Continue to explore u substitution and make sure that that's not something that would make your job a lot easier, especially with these guys. All right. All right, good. We finished early without racing. That's all I really got. The homework, just keep in mind that's going to be due on Monday. So any questions, I'll leave first 5 or 10 minutes of class open for those questions. So if you have them ready to go, and then that'll be due Monday night. Okay. All right, that's all I got. If you have any issues, whatever, you want to stick around, feel free. But if not, then you guys can go. All right, we'll see you Monday. All right, have a good weekend.